Welcome to this explainer. Today, we're diving into the absolute magic of metal extraction. We're going to break down the incredible chemical journey that transforms dry formulas into a fascinating real-world factory tour. Essentially, we're looking at the exact science of how humanity literally pulls the building blocks of our civilization right out of the dirt beneath our feet. So, think about it for a second. How do the raw, dirty materials buried deep underground actually become the sturdy metals we use to build our entire world? I mean, the steel in our skyscrapers, the copper in our smartphones, the aluminum in our airplanes, they definitely don't just spring out of the ground looking like that. They start as dirty, complex rocks. First things first, let's get our terms straight. When we mine these rocks, they're called ores. You can kind of think of an ore like a locked safe that holds our target metal. But as you might guess, these safes are buried in a whole lot of unwanted earthly substances and dirt. Chemists call that useless dirt gangue. So our entire mission here, the whole shebang of metal extraction, is to strip away that gangue and crack open the chemical lockbox of the ore. All right, here is our roadmap for today's factory tour. We're starting with from rock to resource, moving into the Reactivity Rulebook, and then hitting the three major steps: concentration, oxidation, and reduction, before bringing it all home with electrolysis and refining. Let's get into it. Starting us off, Section 1, from rock to resource. This is where we build our baseline understanding of how we actually go about isolating these elements. The core thing to know is that pretty much every extracted ore, regardless of what specific metal is hiding inside, goes through a universal three-step assembly line. First up, we concentrate the ore by getting rid of the physical dirt. Second, we isolate the metal using some very specific chemical reactions, namely oxidation and reduction. And finally, step 3, we refine it to perfection. But hold on, before we fire up the physical machinery, we've got to talk about the rules. Section 2, the Reactivity Rulebook. This is essentially the ultimate VIP list that dictates a metal's fate.
The reactivity series is absolutely crucial here. The most reactive metals at the very top, think potassium and sodium, are clinging to oxygen for dear life. They are notoriously stubborn and demand intense, usually expensive energy to extract. Meanwhile, the metals down near the bottom, like silver and gold, they're far less reactive. They give up their bonds much easier, requiring way less energy to isolate. Honestly, some are even just found as pure elements right there in the earth.
And this hierarchy perfectly maps out our extraction weapons. For those stubborn, top-tier metals, we have to bring out the big guns: expensive electricity in a process called electrolysis. For the middle-tier metals, like zinc and iron, we can use a much cheaper weapon, which is just carbon heating in a blast furnace. And for those least reactive metals at the bottom, well, nature already did the heavy lifting for us. Okay, so before any of that complex chemistry kicks off, we have to execute Section 3, Step 1, concentration. This is all about removing the gangue, the dirt, and we use some pretty clever physical tricks based on the rock's properties. If the ore is heavy, we literally just use gravity and a stream of water to wash the lighter dirt away. For sulfide ores, we use a wild method called froth flotation. We crush the ore, mix it with water and pine oil, and blow air through it. The metal actually rides the oily bubbles right up to the top. We can also use magnetic rollers for magnetic ores or chemical solvents, a process called leaching, to dissolve specific metals like aluminum or gold, leaving the raw dirt behind. Dirt is gone, so we enter Section 4, Step 2, oxidation, where we form metal oxides. Now, paradoxically, to get pure metal, we actually have to force our concentrated ore to bond with oxygen first. The chemical key we use depends entirely on the type of ore we're dealing with. If we have a sulfide ore, we use roasting, which is exactly what it sounds like. We blast the ore with intense heat in the presence of lots of air. But if we have a carbonate ore, like limestone, we use calcination. This is a bit more delicate. We carefully heat the ore in a limited supply of air, or no air at all, to drive off the carbon dioxide gas and leave just the metal oxide. Our metal is now neatly trapped in an oxide state. Boom. We move to Section 5, Step 3, reduction. This is where we actually extract the metal by stealing that oxygen right back. We use what chemists call a reducing agent. For medium reactivity metals like zinc, it's beautifully simple. We just heat the zinc oxide with carbon. Carbon is super cheap and highly effective at this middle level of the reactivity series. It essentially steals the oxygen off the zinc, leaving us with impure zinc metal while releasing carbon monoxide gas into the air. But actually, scratch that. Sometimes carbon just doesn't cut it. Sometimes we use a more reactive metal to violently displace a weaker one. The thermite reaction is a perfect and honestly incredible example of this. By mixing iron oxide with highly reactive aluminum metal, the aluminum steals the oxygen so aggressively that it generates massive amounts of heat. It produces so much thermal energy that the resulting iron is entirely molten. Believe it or not, this exact reaction is used out in the field to weld heavy railway tracks together. It's a real game changer. So what about the absolute toughest bosses on our reactivity list? Let's hit our final section, electrolysis and refining. Highly reactive metals like sodium just won't respond to carbon or simple displacement. They hold on to oxygen way too tightly. So we bring in the heavy artillery, electricity. We melt the metal salt down into a liquid electrolyte and literally zap it with an electric current. This forces the metal ions over to the negative cathode, where they become pure metal. The unwanted elements get pushed to the positive anode and are released as gas. Yes, it's expensive and totally energy intensive, but for the top of the reactivity series, it's the only way to win. Bringing it all together, whether we started with a sulfide or a carbonate ore, whether we used roasting, calcination, simple carbon reduction, or intense electrolysis, all these paths funnel down to one thing: crude metal. Finally, we run it through one last refining stage. This usually involves a specialized electrolytic process to strip away those final microscopic impurities, giving us that perfect, usable purity we need for manufacturing. It's honestly mind-blowing that the soaring skyscrapers, high-speed trains, and supercomputers of our modern era all start with washing dirt off rocks. We built our world by mastering the thermal and electrical rules of the universe. It really leaves you wondering, as our technology keeps advancing, what other untapped elements and miraculous materials beneath our feet are just waiting for us to discover their ultimate chemical key? Keep that in mind next time you see a simple stone on the ground. Thanks for joining me on this explainer, and keep learning.